So what is the St. Petersburg Paradox? This is going to reflect the contradictory reality for probabilistic theories and probabilities on the idea of making a rational choice. The idea that the expected value predicts a course of action, a decision, that no one will actually take because of monetary gain, and the idea of diminishing marginal utility. Now let's talk about the history of the St. Petersburg Paradox. It originated in a paper titled The Specimen Theorizae Novae Dimensora Sortis, which is also known as the exposition of a new theory on the measurement of risk. This paper was written by Daniel Bernoulli, but family drama, and this idea was actually sparked by his cousin Nicholas I. Nicholas I was wondering the following scenario in which he asked Pierre Raymond de Montour. Pierre Raymond de Montour was a French mathematician. He asked him, what is the expectation of B if A promises B to give him some coins in this progression? The progression being 1, 2, 4, 8, 16, 1, 3, 9, 27, 1, 4, 9, 16, 25, or 1, 8, 27, 64. In other words, in which Daniel Bernoulli puts in, what would the expected value attain be if in a coin flip game, an individual flips until the coin lands tails, with each toss that lands on heads doubling the payout. For example, if you have the choice between a 50% chance of winning $100 and a 30% chance of winning $200, you would multiply the probability by the value to find the expected value of your choice. You do this and you find the rational decision would be choosing the $60 one, because this one has a higher expected value. But there is a paradox. So now let's look at the actual paradox, which is going to be shown through this game coin toss scenario. So this is proposed by Daniel Bernoulli, and he states that for each individual toss that lands on heads before landing on tails is going to result in a doubling in the payout. So essentially what this means is that if we were to create a simulation to kind of see this, when the toss lands on tails, and we see that the first toss lands on tail, the second toss lands on tail, and the third toss lands on tail. The first toss, when that lands on tail, you're only going to get $2. Second toss lands on tail, you're going to get a head and then a tail. That'll be $4. Third toss, you get a head, and then a tail. That'll be equal to $8 then. Fourth, you get a head, and then a tail. That'll be equal to $16. So essentially, this is going to equate to the following expression, where you do $2 to the power of k. And k is going to represent the toss number when the first tail appears. And this makes sense because if you're looking at the scenario where you get a tail on the third toss, you're going to do 2 to the power of 3, which is going to give you 8. So now we're going to look at the expected value. Remember, expected value is going to be multiplying the probability times the value. So in this case, if you have the expected value of $2 and then the probability of getting a tail on the first toss would be 1/2. You do that and you keep adding that on to all the different possible scenarios, and you finally get this expression where you do the summation of k equals 1 at the bottom and then depending at the top times 2k times 1 over 2 to the power of k. And this is going to equal to 1 plus 1 plus 1 plus 1 plus 1, which means the expected value is going to be equal to affinity. However, despite that the infinite expected value suggests a rational individual should and could risk any finite amount to play this coin toss game, no rational human would risk a large finite amount to play. And the question is, why? In 1728, mathematician Cramer proposes a reason for this. He states that the decision does not depend on the expected monetary gain. It does not depend on how much money you could receive by playing any finite amount, but it depends on the concept of diminishing marginal utility. Because the marginal utility of a good or service declines as more is consumed, larger amounts of monetary gain reciprocates to a lesser utility. This prompts the actual expected value of the coin toss game to not that be infinite, to actually be finite. So, arithmetically speaking, we see that the expected value of many outcomes times the probability of occurrence cannot exceed the boundary of 2 to the power of m, where m is going to represent the number of flips until the coin lands on tails. And if we also wanted to represent diminishing marginal utility in a math form, it would look like the following equation. We would get 1/2 times the square root of 1 plus 1/4 times the square root of 2 plus 1/8 times the square root of 4 and so forth, and which ultimately is going to show you that we're going to have a decrease in the marginal utility gained. The St. Petersburg Paradox continues to provide insight in decision theory and stresses the importance of diminishing marginal utilities rather than monetary payoffs to explain the paradox.